Hey guys, this is Mrs. Harbin, and this is Pre-Cal, Chapter 3. We are looking at Lesson 3.6, which is all about reciprocal functions. Our life application for this whole entire unit is that you, the student, will see that God's creation displays functions by changing seasons, life cycles, and throughout nature. We're not just learning steps to graph and solve functions. We are recognizing that these functions appear in nature, and as such, we can use them when taking care of nature and taking care of other people. Our lesson objective for today is that you, the student, will identify vertical asymptotes, domains, and ranges of reciprocal functions and graph reciprocal functions. Now, before we get into that, let's review a couple of definitions, like what is a reciprocal? Well, a reciprocal is just a multiplicative inverse. Now, if you don't remember what a multiplicative inverse is, the layman's definition is this. Multiplicative inverses are two numbers whose product is 1 when multiplied together. So the inverse of 5 is 1/5 because 5 times 1/5, two numbers when multiplied together, their product is 1. And then the inverse of f of x would be 1 over f of x. These are inverses. When multiplied together, they equal 1. So hopefully you remember what reciprocals are from algebra. Let's take this then into the world of functions. One thing I do want you to notice, as numbers get bigger, what happens to their reciprocals? Let's think about that. What is the reciprocal of 1? Well, 1 over 1. So 1 and 1, the reciprocal is the same. What about 2? Reciprocal is 1/2. The reciprocal of 5, 1/5. The reciprocal of 10 is 1/10. The reciprocal of 20 is 1/20. The reciprocal of 1 is 100, etc., etc., etc. And what you should notice is that our numbers, as our numbers get bigger, the larger the number, the closer the reciprocal is to 0. We're going to get closer and closer to 0 without ever touching 0 itself. So as our numbers get larger, our reciprocal gets closer and closer to 0. Keep that in mind as we get into graphing these reciprocals. Now let's take a look at the reciprocals of our trig ratios. You have these up on the wall in the classroom, but the reciprocal of secant is 1 over cosine, so those are reciprocals. Cosecant is the reciprocal of sine, so cosecant is 1 over sine. And cotangent is the same as 1 over tangent. Now, just a quick note about reciprocals. Since reciprocal functions do have denominators, you must be careful about what values are used in the domain. What values are used here for x, for example. An undefined function means we're going to have an asymptote. So let's see. If we know that sine, let's say that we do 1 over sine 360, for example, 360 degrees on that unit circle, or if we're doing this in radians, sine of 2 pi. We know that the sine of 2 pi is 0. That would be 1 over 0. And 1 over 0 is undefined. We can't have 0 on the bottom of a fraction. And so if we were graphing this at this particular place on our axis, we would have to put a vertical asymptote because this function doesn't exist at 1 over sine of 2 pi. And so when we're looking at functions, we do have to be careful that whatever numbers we have in our domain for our x value down here don't lead us to an undefined function. Where those exist, we will have some asymptotes, and you'll see more of those in practice. All right, our reciprocal trig functions then, we just talked about what the reciprocals are. Our reciprocal trig functions are y equals secant theta, y equals cosecant theta, and y equals cotangent theta, remembering that secant is 1 over cosine, cosecant is 1 over sine, and cotangent is 1 over cotangent. You will need to memorize those. So let's find f of 1 when f of x equals 1 over 3x to the 4th. This is a reciprocal function. So our f of x would just be, maybe our original function was 3x to the 4th. Okay, and our reciprocal function, which you see here, is 1 over 3x to the 4th. We need to be careful that we don't choose any values of x that are going to make this an undefined function. Let's go ahead and evaluate for f of 1. So in this reciprocal function, when we plug in 1, we get 1/3. Find g of 2 when g of x equals 1 over x squared minus 4. Plug that in, and you get 1 over 0. This is one of those undefined functions, right? If we were graphing this, we would have a vertical asymptote then at g when g equals 2. Find h of 1/2 when h of x equals 1 over 4 to the 1/2, 4 to the x. Go ahead and pause the video, plug that in, and see what you get. Right, when we plug that in, we get 4 to the 1/2, which we can rewrite as 1 over square root of 4. We don't want any square roots on the bottom, so we are going to rationalize our denominator here. And to rationalize our denominator, we are going to multiply both our top and our bottom here by the square root of 4, which gives us square root of 4 over square root of 4 times square root of 4 is 4. Square root of 4 is 2 over 4, which simplifies to 1/2. Now, that's a whole lot of steps that I just took to show you how to rationalize the denominator. We would do that especially when our bottom number, our root, is not a square root. Square root of 4, though, is a perfect square. So we could have skipped all of these steps and just done 1 over the square root of 4, which is just 2, 1 over 2. So I put in a bunch of extra steps in there to show you how to rationalize that denominator in case you get a number that is not a perfect square. All right, let's find k of pi over 4 when k of x equals secant x. All right, we'll plug that in. K of pi over 4 equals secant pi over 4. That we're going to have to go back to that reciprocal trig ratio there and remind ourselves that secant is just 1 over cosine. So secant of pi over 4 is the same as 1 over the cosine of pi over 4. And then using our knowledge here of the unit circle, which we are experts at now, we get 1 over root 2 over 2. We need to get that out of the denominator. And when we do, we simplify that and we get just root 2. If you're not sure how we got from here to here, this is just 1 divided by root 2 over 2, which is the same thing as 1 times 2 over root 2, which gives us 2 over root 2, and then we've got to rationalize the denominator using those steps that I took in the previous example, and that gives us root 2. Let's find the domain of f of x when f of x equals 1 over 3x to the 4th. So we want to see if there are any values that would make our denominator undefined or 0. Any of those would be omitted from the domain. All other values would be acceptable values for our domain. So we're going to take 3x to the 4th and we're going to set that equal to 0 and see if we get any values of x that will give us an undefined denominator. Dividing both sides by 3, we get x to the 4th equals 0. Taking the 4th root of both of those, we get x equals 0. So our domain then would be that x can be all real numbers except for x cannot equal 0. When x is 0, we would have an undefined function there, and we'll have a vertical asymptote then at x equals 0. Remember, an asymptote is that place where the function cannot cross. It's going to be kind of like that invisible barrier, that wall. All right, let's find the domain of g of x when g of x equals 1 over x squared minus 4. Again, we want to know if there are any values that would make this function undefined or 0. So we're going to take the denominator and set that equal to 0. Adding 4 to both sides, we get x squared equals 4. Taking the square root of both sides, we find that x is equal to plus or minus 2. So those are the values that would give us an undefined function. Therefore, the domain for x is all real numbers, but x cannot be equal to or is not equal to plus or minus 2. So again, when graphing this function, we're going to have a vertical asymptote at x equals 2, and then a vertical asymptote at x equals negative 2. And our function will not be able to cross those asymptotes. Let's find the domain of h of x when h of x equals 1 over 4 to the x. Again, we're wanting to know what values of x we can use that will not give us an undefined value. So let's set f of 4 to the x power cannot equal 0. So therefore, our domain is all real numbers. We know that 4 to any number is never going to equal 0. Even 4 to the 0 power is still going to equal 1. And so therefore, our domain is all real numbers. Let's find the domain of k of x when k of x equals secant x, remembering that secant x is the same as 1 over cosine x. All right, so we'll set our denominator here, cosine x equal to 0. And then we're going to think about our knowledge of the unit circle. We know that cosine is 0 when x equals pi over 2, that's at 90 degrees, 3 pi over 2, that's 270 degrees, 5 pi over 2, etc., etc., etc. This is a sequence, and the sequence repeats every pi. So we would write that as cosine of x equals 0 when x equals pi over 2 plus every 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, whatever the number is. K represents those integers. So it's going to repeat every pi, and that's how we would note that. Our domain then would be written that x is all real numbers, but x cannot equal to pi over 2 plus integer times pi, however many times that might be, where k is an integer. So that's how we would denote that domain. Just a couple of reminders. Remember that x to the nth power and x to the negative nth power are reciprocal functions. If we put some numbers in here, x squared and x to the negative 2 are reciprocal functions. X to the negative 2 is just written as 1 over x squared. So you can see that x squared and 1 over x squared are reciprocal functions. So remember that x to the n times x to the negative n equals x to the 0, which equals 1. And according to our definition of reciprocals, reciprocals are two numbers that one